where you don't ask it to do something and then it does something. So it's basically just a chat bot that does something. You'll be like, hey, can you like update this like server? But yeah, sure. And then people work into the log and then nothing will go through. It's like, you didn't do this. Like, oh, I'm sorry. And then nothing happens. It's like, yeah. I'm trying to like understand this. One of my things is like, you're right. That's my bad. I was like, I just
Same thing.
I was just like, you know what, I'm like, I've done enough homework for today.
I hate that.
And like, I've actually done enough homework for today.
More bad.
You know what, you're right, I'm just gonna cut to it, do it this way. It's like, you're not doing this. The same thing you told me.
We have my senior player's child.
That's a sick name for the senior.
He is a Chad. No, he's great. No, not. He actually just got diagnosed with adult onset diabetes.
That is
He had co-pilot, like, I don't know what he did. He had like a whole just like series of prompts. And he got it like open after like commit like 26 tasks and open up the guard. And you commit incrementally. And it was like dynamic native like background by itself. And just
you guys use your DevOps tools. Yeah, I was gonna say, I'm like, SQL guy versus SQL guy right now. Fine.
Oh, okay.
Okay, good morning, everyone. I want to welcome you to another Applied Multivariate Statistics class. Before I get started today, I actually want to tell you that I attached a material that I call miscellaneous. This material actually contains some arrow quotes and homework one useful arrow tips. So the material is already on Canvas. Okay, so but I quickly want to walk you through that material because of the ongoing assignment. Okay, so you can see you have Iris data that is multivariate in nature, and of course maybe what you want to do is to construct a scatter plot, the scatter plot matrix. Okay, the scatter plot matrix is actually going to look like that. Okay, and if I don't want repetition, okay, this is if I only want to consider the upper trigonal aspect of that. Okay, you can see codes. These are codes that will help you. Okay, so take a look at that. And if I want to add correlation values, but I remember in the ongoing assignment, I asked you to add correlation values. Okay, you can see this code here, add correlation on the lower panel and stuff like that. You're actually gonna have this result. You can see correlation value now. Okay, so there's another one. There's another one. You can see on this one has colors. Okay, so if you practice the codes here, okay, that will go a long way. Uh, helping you in the current or the ongoing homework. Okay, I put a lot of and there, if you really want to enjoy this the more, you can load a package called Libra, call it Psych, PSYCH. Okay. Now, if you take a look at this code now, look at what is going to come out of the code. Now, on this one, I actually have a combination of a scatter plot and histogram. Okay, the histogram, as you can see, the histogram is what you have in the diagonal. Okay, you can also see the scatter plot, then you can see the correlation values as well. So if you go through the codes, that will go a long way, okay, in helping you out on the assignment. Okay, that's a lot of code here. Take a look at that. Okay, so I will advise you practice this. So I already published this on Canvas. Okay, so I'm gonna stop uh so I can, you know, share today's what I have for you today. Uh among those that are attending online, can somebody confirm if you are hearing me clearly? Those of you online. Those of you online, I want to be sure you are hearing me clearly. Can somebody talk that you are hearing me?
We can hear you.
Thank you so much. If somebody is going to attend lecture online, I want us to be as interactive as in person because my experience shows that some people can decide to log on to the Zoom and they're going to be far away from the Zoom. So I want you to be, I want everybody to be around. Thank you. Okay, so I'm actually going to share my screen for today. Okay, I want to welcome us to today's class. We're going to be focusing on matrix algebra. And let me say this, what we want to do today is very crucial to the analysis of multivariate data. Uh, because the fact that the multivariate data is is arranged in row and columns, the idea of matrix can actually be used. And that's why my intention today is just to remind you of matrix algebra. Let me tell you this. So for those of you that are doing masters or PhD, if you have issue with statistics, then I would say you have issue with maths because you need knowledge of matrix algebra to be able to navigate your paths in multivariate analysis. So because of that, I welcome you to matrix algebra. We got a lot that we're going to talk about, some of you will be wondering, why am I interested in this? Why, since I can make use of my software. But let me tell you this, software is not going to work if there is no formula program behind the scene, okay? You need to be able to understand the way the formula that will program behind the scene work. And let me also say this, it is only when you understand the formula behind the scene that you can also improve on the formula because what is permanent in life is change. We want a situation whereby uh, our model that we apply actually commiserate with reality. Okay, and reality changes. We don't want to use a static model for a dynamic situation. And that's why we need to be able to understand the conventional method that we have. And that will give us an opportunity to be able to improve on that. So I'm going to walk you through some mathematical operation involving matrix because all of that will be in display in the analysis of multivariate data. So, number one, I'm going to talk about basic definitions, vector, matrix, the transpose and trace, symmetric, diagonal, and some special matrices. From there, we're going to talk about how we can perform algebraic operation on two different matrices or on two different vectors and so on like that. And of course, lastly, we're going to talk about matrix decomposition. because they are when we have an ambition of processing an image, okay, uh you actually you have an image, okay, and because image actually has a lot of pixels, and because you want actually to preserve your storage or facility, okay, and you now want to compress your image in such a way that the originality, the quality of the image will not be totally affected. Because why are you trying to compress an image is because of the fact that you do not have enough storage space, okay, and you now want to reduce, that's what we call image compression, and the idea of matrix decomposition is actually going to be used. Because why matrix decomposition for image? Because image has a dimension. Every image is a matrix, okay? And that's why the idea of matrix decomposition is going to work. This is what I used to tell students. If you are doing maths, try to relate your maths. We don't just do what we do. There's a reason why we do what we do. So before I start this right now, I've already given you a background. Why do we need this? Okay. If you don't understand why you do maths, I will advise you don't do maths. I don't want to waste my time, even though I know how to figure it out analytically. But what is the sense behind it? Okay. Now let's get started with the basic definitions. The first page. We can have, this is actually what we call a vector, okay? And this is what we call a one-dimensional array, okay? A vector or a column like this can be used to showcase different means, okay? Means across variables, okay? Now, this is what we call matrix. If you take a look at this, a matrix is going to be in row and column. That's a typical of how the multivariate data set look like. The multivariate data set that you have in row and column. Okay, now the dimension of this matrix is the numbers of rows multiplied by the numbers of columns. So the numbers of row is denoted as n, while the numbers of column is actually p. Oh, let me do this. Okay, so it's actually p. Okay, so I just wanted to recognize that. I want to go to the next page. We want to talk about the rank of a matrix. Let me tell you this. When you are dealing with estimation of parameter in linear regression, has anybody heard about linear regression model? Okay, so if you are dealing with the estimation of parameters in a multiple linear regression model, okay, you normally use formula. Give me 1 second. I think I'm gonna write. You normally use let me see if that is writing. Okay, so you normally use a formula beta cap equal S transpose S inverse, okay, S transpose Y. Okay, now let me tell you this. Before I can actually find the inverse of the S transpose S, I'm actually expecting the determinant of S prime S to exist. And let me tell you this, only condition under which determinant of S prime S is going to exist is when the matrix has a full rank. What do I mean by a full rank? If I have a 3 by 3 matrix, I'm going to say that again. If I have a 3 by 3 matrix, the rank of that matrix should be 3. If it is 3, then the matrix has a full rank. What do we mean by that? It means we have the number of independent rows and the numbers of independent columns. We expect the variables that are arranged in column to be independent. If they are independent, if independent occur, of course, we expect to have a full rank. But situation where a particular column depend on another column, then we're not going to have a full rank. If you don't have a full rank, there's going to be an issue in estimation of parameters in linear regression model. Okay, so, and that's why I want to talk about, full rank. I want to talk about rank. Okay, now I need you to pay attention to this. When we talk about rank of a matrix, we can talk about column rank, we can talk about row rank. When I talk about column rank, I'm actually talking about the variables in the columns are linearly independent. When I talk about row rank, okay, then I'm trying to say the row are linearly independent. Of course, when I talk about row, talking about observations, it could be persons. I'm expecting them to be independent as given, that's one of the assumptions in statistics. But you know what? It depends whether you're going to have a full column rank or you're going to have a full row rank. It depends on the number of observations and the numbers of features. But you know what? Let me do this. Take a look at this. If I have a multivariate data set with n number of observations and with p numbers of features, and if a full rank exists, then the full rank should be the minimum of the number of observation and the features. Now, if the number of observations is the minimum, that will serve as the rank of the matrix. If the P is the minimum, that is going to serve as the rank of the matrix. But you know what? Specifically, I want to talk about when are we going to have, number of observation to be a row rank. That is a situation where the number of observation is less than the numbers of features. When number of observation is less than numbers of features, that is high-dimensional data. In high-dimensional data, the numbers of features is more than the number of observation. In that situation, the full rank is actually going to be the number of observation. You know why? Because the number of observation is the minimum in that instance, because the numbers of features is more than that. But situation where the number of observation is actually greater than the number of features, then we actually going to have a full column rank. And in that category, in that situation, the P, the number of features will be the full rank that we talk about. Okay, you know, statistics is like a story that goes on and on and on. Now let's go to an example on data set. We could have a matrix that has a full rank, okay, where a full rank exists. We can also have a matrix where full rank does not exist. I wanted to take a look at this matrix. I got two columns, right? But I don't believe that these are independent. Because when you look at the first column, please pay attention. When you look at the first column, I can figure out the second column from the first column by multiplying every element in the first column by 3. If I multiply 1 by 3, that will give me 3. If I multiply 2 by 3, that's going to give me 6. If I multiply 3 by 5, which means the relationship is this. Whenever I have this kind of relationship where a particular column can be figured out from the other column, that matrix will never have a full rank. Okay, because they are supposed to be independent to have a full rank, but right now they depends. Okay, I just wanted to take notes of that. But you know what? Let's take a look at this guy. It's another matrix. Okay, if you take a look at this matrix, when you take a look at the first column, okay, and the second column, the fact that even if you look at the first one, if I multiply 1 by 3, that will going to give me 3. When I multiply 2 by 3, that's going to give me 6. But when I multiply 4 by 3, that will not give me 15 because of that violation. Then I'm actually going to say there's possibility that is going to have a full rank because not all the entries, okay, that depends on the other one. That's exactly what we mean. Okay. I'm actually going to move. Okay, go ahead. Here. Oh, yeah. Do we have one? Oh, okay. So if you take a look at this one, we don't have a full rank. Do you know why we don't have a full rank? We do not have a full rank because, oh, sorry, we have a full rank. We have a full rank because not all the entries in the second column depend on the first column. Or if you take a look at here, if you look at this one and this one, we establish this relationship. Every entry in the first column, if I multiply by 3, automatically going to give me the values in the second column. With that, that depends. That is not going to have a full rank because when we are defining full rank, we're saying columns, they should be independent. Rows, they should be independent. Okay, so this is what happened. You know, something may not be a full rank in general, but it could be specifically maybe a full row rank, okay, or a full column rank. Okay, does that make sense? So it's possible. Okay, now I'm actually moving now. I want to go into transpose. There are some other basic manipulations that we do when we're working with matrix. Okay, we can transpose a vector, we can transpose a matrix. Transpose actually means changing position of elements in a matrix. Is a way of converting row to columns or converting column to row. So if this is a column matrix, okay, when I put that, that means transpose. Then I'm converting that to row. Then it means I'm also changing the dimension. Initially, it's n by 1. It's going to be 1 by n. That's for vector. Okay. And we also do that to we also transpose a matrix. Okay. A matrix of n by p, when we transpose that, it's going to be p by n. What you're going to see is this guy here. Okay. It's now going to be here. It's like converting the row to column, or you're converting columns to row. So transpose or transposing a matrix is very, very crucial process in the analysis of multivariate data. Okay, now I want to go to an example. Please pay attention. Okay, take a look at this. I have a matrix of 4 by 1. Oh, sorry. I have a vector. Okay, and this is the transpose, converting the row to column. Okay, now if I want to apply that to matrix, this is a matrix of 4 by 2, and this is the transpose. Okay, transposing is changing position. Any question before moving? Okay, now in the absence of question, I'm actually going to move. Okay, let's come here now. Let's take a look at properties involving transpose in case I have more than 2 matrices or vector. So there's something, if you take a look at this. When I do the transpose of a transpose, then it's going to return me back to the original matrix. Does that make sense? Okay, that's what that guy is talking about. If I have 2 different matrices, okay, and I had 2 matrices together, I do the transpose, is the same thing as adding the transpose of each. You can verify this. Okay, you can verify that. Now, if you take a look at this property, if a B is a scalar, at times we use a constant number to multiply matrix. Okay, if I multiply a matrix by a scalar and I find the transpose, it is the same as multiplying the scalar by the transpose of a matrix. You can actually verify that. Now, if I do a matrix product, I got 2 different matrices, I multiply them, and I find the transpose of the resulting matrix, it is the same thing as finding the product of the transpose of B and the transpose of A. All these properties can act, they've been mathematically proved and statistically observed. So if I were you, you can just give an example and see whether that can be verified. Okay. Now, another property is this. If I find the inverse of a matrix and I find the transpose of the resulting matrix, it is the same thing as finding the inverse of the transpose. Okay, I just want you to now why do I need these properties? Because these are kind of rules that guide matrix operation, and we need to be guided by these rules. Okay, now I want to leave transpose. I want to go to trace. Now, trace is very, very crucial. When we talk about particularly uh, in principal component analysis, where our intention is to reduce dimensionality in the data set. Okay, the idea of trace actually work. Okay, because the focus is explaining total variance. Okay, when I have a covariance matrix, the diagonal of the covariance matrix actually give the variances. I want to believe you understand. You know that the diagonal of covariance matrix. Okay, I'm actually going to have the variance of the first variable, the variance of the second, and so on like that. If I'm interested in total variance, the total variation, then I'm going to add up the element in the diagonal matrix of the covariance matrix. When I'm doing that, I'm actually doing trace. If I have a matrix like this, take a look at this, and particularly a square matrix. Don't forget, covariance matrix is a square. It has to be a square matrix. Okay, when I add up this guy, element in the diagonal, then I'm doing a trace. And that's why take a look at this. The trace of a matrix A is adding up elements in the diagonal matrix. Okay, that's what we mean by trace. Can we also have properties? Oh, let's have this very simple mathematical example before we go on. We have a matrix A given like this, and I want to find the trace of that. The trace of that is just, okay, you know what? Add up this guy. This is exactly what we're doing here. So the trace of a matrix is addition of elements in the diagonal of that matrix. Now, you know what we want to do now? Since you understand the basic operation of that, can we look into properties of trace, matrix trace? Okay, please pay attention. If I have a matrix A, I find the trace of A, I find the trace of the transpose, they should be the same. Because let's come back here. Do you know that if I find the transpose of that, okay, the element in diagonal, even if they're going to change, the addition will still remain the same. You can try it out. Okay, it's going to be the same. It's going to be the same. So that's why this is already verified. Okay, you can try it. Okay, you have a matrix A, you find the transpose of that, then you now try to add elements in the diagonal of the two matrices, you're actually going to get the same result. Okay, that's what it means. Now, another one here. If I have two different matrices, matrix A and B, and they are conformable for addition, because they have to be they have to have the same, they have to be in the same dimension before they can be added up. Okay, when I add A to B, matrix A to matrix B, and I find the trace of the addition of two matrices is also is the same as the addition of the trace of each matrix. You can verify this. Okay, if I'm actually using a scalar here is a lowercase b, maybe like 5, 7, or -3. I want to use it to multiply a matrix. Okay, now if I use a scalar to multiply a matrix and I find a trace, then it is the same as multiplying the trace of that matrix by the scalar. Okay, now what about when I'm talking about matrix multiplication, where I multiply matrix A by matrix B? Okay, and because let me tell you this, uh AB in matrix may not be equal to BA. Okay, but uh the trace of the product of A and B, we're always going to be the trace of the product of B and A. I just wanted to take note of that. Now, lastly, on this page, how does this concern statistics? How does it really concern multivariate statistics? I needed to pay attention to this. By the time we start principal component analysis, okay, because in principal component analysis, we have so many variables and we want to reduce our dimensionality. Okay, we want to reduce the dimension in the variables, and we're trying to create artificial variables that I call new dimensions, and those variables that we create will be less than the number of features that we have initially. We expect each component that we're going to derive to have a variance. The name of what is the name that variance is called? The variance of a principal component, it is called eigenvalue. Okay, by the time we start, you actually, so the eigenvalue represent the variance. Now, which means in the diagonal, in the diagonal of the matrix, we're actually going to have lambda 1, lambda 2, lambda 3, and so on like that. And the trace of that of matrix A will be the summation of the lambda j. Okay, where each lambda represent eigenvalue. We're still going to talk about all of that. But let me tell you this. Uh, we have a condition here. The condition is that the matrix we're working with should be symmetric. What do we mean by symmetric matrix? Okay, by symmetric matrix, particularly when you look into covariance matrix, it has to be symmetric. Symmetric means when I have a matrix A and I find its transpose, okay, it still look the same as A. Changing position doesn't really change anything. Okay, so that is what it means. So it has to be symmetric. Okay, I'm moving now. Okay, and I want to talk about symmetric. Okay, if I have a matrix A and I find the transpose, then it should look exactly the same as the original. When I change the position of a matrix from row to column, okay, and the resulting matrix still look exactly like the original, then I'm actually going to say that kind of matrix is symmetric. Okay, and I'm actually going to say this. Covariance matrix, an example of a symmetric matrix. Okay, now let's have an example. Okay, let's have an example. Okay, if you take a look at this guy, it's symmetric. If I change, how do I know? Take a look at this. If I change this guy to column, look at that. It's still that, right? If I change that, okay? So this is symmetric. But I need you to take a look at, oh my God, look at this guy here, 9104, but this is 9103. That's not symmetric. Does that make sense? That's how to know. Okay? So this is an example of 4 by 4 matrix. One is symmetric, the other one is not. Okay, now I want to come to diagonal matrix. by the time we start, there's something that we call singular value decomposition, okay, in image processing, okay. We're going to talk about the number of singular values that normally occupy the diagonal of a matrix. Now, when I talk about diagonal matrix means I got a matrix that, that it has some numbers, some numbers in the diagonal, but in the off diagonal, all numbers in the off diagonal is zeros. All numbers. Where is the off diagonal? This is off diagonal. This is also off diagonal. All numbers in the half diagonal, zeros. But in the diagonal, at least we're actually going to have a number that is not zero. Okay, this is an example of a diagonal matrix. Okay, so when we talk about diagonal matrix, we're actually saying, okay, in the half diagonal, all elements are zeros. But in the diagonal, at least one element is actually non-zero. So this is an example of a diagonal matrix. Now, and I want to tell you this, identity matrix is a special form of a diagonal matrix. Okay, in the off diagonal, you have all elements to be zeros, but in the diagonal, before it can be classified as an identity matrix, all entries has to be one. Okay, take a look at this guy now. All entries in the diagonal has to be one. The moment one of the entries is not one, then it's just going to be called diagonal matrix. It's not an identity matrix. So this is an identity matrix of P by P. When I say P by P, I'm actually saying a square matrix where the numbers of rows and the numbers of columns are the same. So identity matrix is a special form of a diagonal matrix. If you really want to understand your statistics clearly, I think we need some basic knowledge of mathematics because we live the world mathematically. Okay, the world is mathematical in nature, and that's why we need the knowledge of maths. Okay, now I want to move right now to something else. Take a look at this. I want to talk about zeros vector. I want to talk about zero matrix. I want to talk about one vector. So I want to talk about one matrix. Because at times, if you take a look at this guy now, okay, there is possibility in a column of a vector, all the entries are zeros. There's possibility that we can have means to be zero. Mean can be zero. Maybe you're trying to say the mean from different variables, zero, okay? And we can also have a matrix where all elements, including the diagonal and the half diagonal, they all going to be zeros. But that would be a special matrix anyway, okay? And we can also have a vector where all entries all of them going to be ones. If we have one, we're going to call that one vector. And we can also have situation where all entries in a matrix, all of them going to be one. Okay. Now, there's something I needed to see here. This is not a square matrix because the numbers of rows and the numbers of columns are not the same. How do I know? They say n by p. Okay. And let me tell you this, there's possibility, we could have a square matrix where they all have zeros. We could have a rectangular matrix where they're also going to be all zeros. Okay, now, since you understand that, let's go into basic calculations. Okay, now, I want to go into basic calculation now. Now, we are now on objective number 2. Basic calculations. So what we're going to talk about in basic calculation, how do we actually add two matrices? How do we subtract? How do we do products? Okay, let's get started. Okay, I have a matrix A and I have a matrix B. Okay, if I have a matrix A and I have a matrix B, and if all elements in one matrix is exactly the same as element in the other matrix, then I'm actually going to say they are equal. That's what we call matrix equality. With that, I'm actually going to say matrix A equal to B because all entries are equal. Okay, but situation where there's only one, even though every other element are equal except 9 here and 0 here, then I'm going to say the two matrices are not the same, even if majority of the entries, okay, matches, but except one, then they are not the same. So this is matrix inequality and matrix equality. Okay, I'm actually moving. Okay, now if we don't just do what we do, we got a reason why we do what we do. If I want to perform basic matrix operation, we need rules. There's a rule that guide us. I want to add two matrices together, or I want to subtract two matrices. Before I can do that, they have to be in the same dimension. The numbers of rows have to be of this matrix has to be the same as the numbers of rows of the other one. The numbers of column of this matrix also have to be the same. Now, let me show you an example. Take a look at this guy. I got a matrix A, and I got a matrix B, and I want to do A plus B. Because these two matrices, they are in the same dimension, operation of addition can take a center stage. So if I'm going to add, I'm actually going to be adding elements in the corresponding position. Okay, can you see that? And that's what I have this guy here. Finally, this is the result of the addition. Now, I'm going to do the same when I want to perform the operation of subtraction. Okay, now you can see if I want to do that, it's going to be 1 minus 5, 4 minus 6, okay, 8 minus 1, 13 minus 7, and so on like that. That's what I have here. And this is the result. Because at times, we may want to look at the difference between multivariate data set coming from two population. We want to look at the difference, okay? Okay, so we may want to do that. Okay, now that's for the addition and subtraction. I'm actually moving. I want to go to what I call vector inner products. Okay, this is one of the example of a cross product. And this is if you take a look at S prime Y here, this is part of the components in multivariate linear regression model. Okay, I have I first find the transpose of S before multiplying by Y. Okay, now this is X prime and multiply by Y vector. If you take a look at what I have here, this is more or less like X times Y1, S2 times Y2, until we get to Sn times Yn. If I have x1 times y1 plus x2 y2 plus, that is the same thing as having that sum of xi yi. Okay, sum of si yi, which we call summation xy. Okay, in covariance analysis, in linear regression analysis, of course, we can rule out summation of xy, sum of the products. Okay, now here I do s prime y. Okay, we can also have a situation where we use a matrix to multiply the transpose. Okay, so this is an example. If this is x prime, okay, the transpose is that. Okay, now, and this is, if you take a look at this guy, so the S prime here is this guy here, the row one, and the Y is the column one. So what I'm trying to say, if I want to multiply, so this is gonna go with this guy, that guy is gonna go with that guy, this one is gonna go with this, and this is gonna go with that. Then I'm gonna add them up. And that'll give me 7. Okay? So take a look at that. Now, this is vector outer. There's 2 cross products. Look at the first one. This is inner one. The inner is when I use the transpose to multiply the other one that is not transpose, we're going to call that one inner. What about the outer one? The outer one is when I use S to multiply the transpose. So take a look at that. Okay? This guy here. And that's what that, if you take a look at this is going to give us this. Okay? So if I were you, why can't you can revisit that, okay? So try to revisit that. Okay, now it's an example of the outer one. If you take a look at that, when I have X without a transpose, it's going to be a column. Okay, with the one with a transpose, it's going to be a row. Okay, if I want to multiply, of course, this is going to be the result when I multiply at the end of the day. But you know what? In this course, you do not need to use a manual way of doing that. It's going to waste your time. Of course, you can make use of software to achieve this. Okay. Now, we have a matrix scalar product. In a matrix scalar product, you are using scalar to multiply a matrix. That's why the scalar here is B. That's why in the matrix, you can say B, 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 all true, because B is a constant. It's a scalar. Okay. So we can have that kind of situation. Now let's look into the example. If I have a matrix A and I have a scalar B equal to 2, and I want to do the multiplication, it's just to use 2 to multiply a single element in the matrix, 2 times 1, 2 times 4, and so on like that. That's going to give me this. Done. Okay? Now, let's move to this. We can also have a matrix vector product. Okay? Where we have a matrix and we have a vector. A vector can be a column vector or a row vector. So this is multiplying them. We're actually going to use this in a linear equation. Probably when we are dealing with a graphical lasso, dealing with principal component analysis, which is a linear combination of features. This is going to take a center stage. Okay, so multiplying a matrix by that, okay, I'm actually having this result. Okay, like I said, we have a way to do all this in R. Let's look into an example. This is a matrix. This is a vector. I want to multiply a matrix by a vector. This is the matrix. This is the vector. So if you take a look at, before I can use a matrix to multiply, I have to ensure the number of columns has to be equal to the numbers of row here. How many columns do we have here? 1, 2, 3. Okay, we got 3 columns. How many rows do we have here? 1, 2, 3. Then they are conformable for multiplication. Okay, if I want to do the multiplication, do you know what I'm going to do? Oh my God, 3 is going to go for that. Okay, 4 is actually going to go for this, and this is going to go for that. Then I'm going to add them up. Can you see that? Then I'm going to do the same. 4 is going to go for 1, 7 is going to go for that, and at the end of the day, this is what I got. Okay, now we can have a matrix by matrix product. Okay, this is a matrix. This is another matrix. Multiplying them, this is what we have. But let me tell you this. A multiplied by B may not be the same as B multiplied by A because commutativity may not hold. This is an example of using a matrix to multiply a matrix. If I were you, you can visit that. Okay, at the end of the day, you're going to get this result. Okay, because of my time, that is going to be the last page. We can also have situation where we are multiplying by identity matrix. Don't forget, when I say identity matrix, okay, in the diagonal element, we're going to have 1, 1, 1, 1. but in the off diagonal is going to be 0. Identity matrix is more or less, to me, is looking like 1. Okay, so if I multiply a matrix by an identity, I'm actually still going to have that matrix. It's similar to multiplying 5 by 1. 5 times 1 is 5. 7 times 1 is 7. Multiplying a matrix by identity is actually going to give me that particular matrix. Okay, or multiplying identity by matrix is still going to be the same. Why are we doing this? Let me tell you this. It is not a waste of time to go over, you know, in this mathematical operation, because what we program in the software, okay, these are the idea that we program in the software. But let me tell you this: what we have in life, things are changing in life. Okay, now if you understand the conventional approach, then you will be able to know how to modify or how to reparameterize the existing methodology, to be able, to commiserate with the reality, because the reality keep on changing, and we are not going to rely on the approach that we have been using for years. And that is why we need to be able to understand, basic mathematical operation. Let me tell you this: without algebra, we are never going to have statistical methodology, because the knowledge of algebra was actually used to derive those methods that we use today in statistics that are actually doing a fantastic job. And that's why we needed knowledge, basic knowledge of mathematics. This 9:55 is where I'm going to stop today. Is there any question, or whether in person or online? Okay, so in the absence of question today, make sure you all stay safe and have a lovely day. See you on Friday.